You have your student joining with you as well, Professor Jeriel. Let me see the screen. Professor Jeriel, can you hear me? Professor Jeriel?
Yes, ma'am.
Yes. Can you please share the link with your students as well, so your student can join us? Thank you.
Yes, ma'am. I have already done that.
All right. Thank you so much.
And have requested them to join in a while.
Very good. Thank you. Good afternoon, Miss Kay. How are you? Good afternoon, Miss Kay.
Hi,
How are you?
I'm good. I'd love to, I'll be here for a couple of minutes because I have a meeting with the president at the 2:15, but I'm just gonna keep the Zoom video on.
All right. Thank you so much for joining. I understand you are very busy. And thank you for replying my email even during the weekend.
No worries about that one. To all my inquiries too, I sent you a message during the weekend and you also replied. Thank you, Dini.
You're most welcome. Yes. It's just part of our job. Sometimes during weekdays, since both of us are lecturer, you are also teaching, I'm also teaching, then everyone is busy during weekday, then during the weekend, then we find time
Yeah.
to reply all the emails. Yeah. Thank you. We are still waiting, some of them joining.
Sopoy. Sopoy.
All right, once again, good afternoon, everyone. I'll begin this lecture. Okay. Hello, everyone. Good afternoon. Greetings from University of Merdeka, Malang. I hope all of you are doing well. My name is Andini Riswandini. I am your moderator for today's international collaborative teaching with the topic of solar energy, photovoltaic, and technical elective subject in mechanical engineering. This event is proudly presented to you by the collaboration of Office of International Affairs, Faculty of Engineering from University of Merdeka, Malang, and Central Philippine University. Please allow me to extend our warmest greetings to Vice Rector 3 for Student Affairs from University of Merdeka, Malang, Dr. Widiharsa, Vice Rector 4 of University of Merdeka, Malang, Dr. Sunardi, to the Dean of Faculty of Engineering from Central Philippine University, Dean Danny Molina, to the Head of Office of International Affairs from Central Philippine University, Ms. K. Adenkayo, MED, to the esteemed speakers of today's international collaborative teaching, Mr. F.A. Widiharsa, SDMT from University of Merdeka, Malang, to Professor Jeriel G. Militar, PME from Central Philippine University, to our students from the Faculty of Engineering from University of Merdeka, Malang, and to the students from the Faculty of Engineering from Central Philippine University. It is my pleasure to welcome all of you to University of Merdeka, Malang and to this lecture. For all the participants, we will have the Q&A session at the end of each presentation. Please kindly type in your questions in the Zoom chat box. Kindly state your name, where you come from, and followed by your question. Now, as we have come to the main event of this lecture, please welcome the first lecturer, Mr. F.A. Widiharsa, STMD from University of Merdeka, Malang. He is the senior lecturer in the Faculty of Engineering. Mr. Widiharsa, without further ado, the time is yours.
Thank you, Budini, for the opportunity.
You're most welcome.
Good afternoon, Professor. Good afternoon, my friend, my colleague. Good afternoon, everybody. How are you doing all?
We are good.
I hope you guys doing well. I'm very glad to meet you, all of you, in this opportunity. Please let me introduce myself. My name is Franciscus Asisi Widiharsa. Usually people call me Widi. In this discussion, we're going to talk about renewable energy, especially in solar energy, focusing in photovoltaic. Now I'm trying to share my PowerPoint. Okay. In any discussion about climate change, global warming, and energy crisis, it is often about need of green, clean, continuous, and sustainable energy as alternative solution. It's called renewable energy. For example, sunlight and wind always shining and blowing. For the table one, you can see that Indonesia also take this transition energy seriously by making a target for the utilization of the renewable energy. About 33% in 2025 and 31% in 2040. That is the target. From table number 2, you can see Indonesia, the biggest potential of solar energy. Target using the renewable energy is 23% and 31% in 2050. And this is our chance to know, explore, and make development about it. Now we need to get about solar energy. Solar energy is one of renewable energy sources that come from the sun. This energy can be converted to thermal and electricity. The conversion of energy from sunlight into electricity, either directly using photovoltaic equipment or conversion to thermal energy using concentrated solar thermal collector or flat plate collector. Photovoltaic cell convert light into electric current using the photovoltaic effect. The target for utilization is 3%, 6,000 megawatt of the existing potential. I said before, solar energy is one of renewable energy sources with largest potential, 46%, around 200,000 megawatts. The target existing potential in 2025, now installed solar power plants about 91 megawatt. Utilization is still small, below 0.1% in August 2021. And now, next is solar irradiance. So how solar irradiance reach the Earth's surface? When the sun shines on the Earth, before it reaches the surface of the Earth, there are clouds, and some are reflected, some are absorbed, and the other transmit. When radiation is reflected and scattered, it's called diffuse radiation. Some go directly to the Earth's surface, it's called beam radiation. And some of diffuse and direct is called total or global irradiance. For solar cell or solar panel application, we need only beam or direct irradiance. Diffuse irradiance still can use for the flat plate collector thermal application because the radiation can be absorbed by black body plate. The type of the irradiance, beam, diffuse, and total. And next we go to the measurement of solar irradiance. We have two measurement in my laboratory now. And we know if solar irradiance is amount of light energy that received by surface per meter each second. It's also called flux or intensity of solar radiation in watt per square meter. Solar irradiation can be measured by solarimeter and pyranometer. Solarimeter measurement results are lower than pyranometer. Pyranometer more sensitive than solarimeter, especially when there is no direct sunlight. Why? Radiation received by pyranometer with a principle of black surface. And radiation received by a solarimeter that use silicon cell. So the pyranometer measure the global radiation. And solarimeter only measure direct radiation or beam radiation. This is the classification of the solar energy utilization. Solar energy utilization can be classified by two types, direct, indirect method. Indirect method means solar energy applied to water, wind, biomass, sea water temperature difference, and direct method in thermal and photovoltaic. In thermal, we need a collector heat to collect thermal energy from the sun and convert to heat, air, or water. In photovoltaic, we need solar module to convert solar energy to electricity. Now we see solar thermal collector commonly divided in two types, flat plate and concentrator. Such as flat plate and concentrated collector. Where the flat plate collector utilize principle of black body surface for absorbing the heat from the sun to absorber plate and to fluid pipe. And concentrating collector used for converting solar energy into heat energy, and the radiation emitted by the sun is optically concentrated using mirror lens before converting into heat. This is example of solar thermal collector, which is flat plate collector. This collector is commonly used. It has simple design. Solar collector flat plate typically consists of main component such as flat absorber, fluid pipes, fixed to the absorber plate, which is the liquid to be heated flows. Insulated material, glass cover, glass frame, and side frame and lower frame. That is a main element of the solar flat plate collector. Insulation material is for covering bottom side and collector, reduce head losses. Now I will explain how the solar and flat plate collector works. Fluid comes to the bottom header and then flow through the flow pipes and being heated by flat absorber. Then exits through the upper header pipe with higher temperature. And now we're going to talk about the solar cell, a process that generates voltage and electric current in a photovoltaic cell when it is exposed to the sunlight. The photovoltaic effect was discovered by a French scientist named Edmond Jeriel in 1839. Solar cell is made of two types of semiconductor, called P-type and N-type silicon. The P-type silicon is produced by adding atoms as boron that have a less electron in their outer energy level, because boron has one less electron and required to form bonds with the surrounding silicon atom. The electron vacancy or hole is created. And the N-type silicon is made by adding atoms such as phosphorus that have one more electron in their outer level. Phosphorus has 5 electrons and its outer energy level. Its bond is a silicon neighbor atom, but one electron is not involved bonding, so it's free to move inside the silicon structure. This causes electric field in PN junction, photon, and produce electricity. A solar cell is an active element that utilizes the photovoltaic effect to convert sunlight energy into electrical energy directly. Each cell measuring 10 centimeter times 10 centimeter at peak condition able to produce current 3 amperes, voltage, electric voltage 0.5 volt, and power 1.5 watt. Several solar cells connected in series will have a higher voltage. For example, connected 33 cells will produce a voltage of 16.5 volts, 33 times a half volt. The combination of several solar cells connected in series is called solar panel or solar module. Now, there are sometimes types of panel we use to utilize solar energy. There are monocrystalline, polycrystalline, and thin film. Monocrystalline is made from single crystal of silicon, and polycrystalline that consists of several crystals of silicon in single PV cell. Thin film solar panel are made from amorphous silicon, which is a non-crystalline silicon. In the market, monocrystalline solar panel are highly efficient that have designed smaller area but come at higher price and higher efficiency than polycrystalline or thin film solar panel. The characteristic of solar cell are expressed by a relationship between voltage and electric current. Testing the characteristic of solar cell is carried out by providing variable load with the following circuit. For constant radiation flux, will give the ampere and voltage characteristic curve. The curve happen for the test. In real life, the flux radius will keep changing. When the voltage is low or zero, the current is maximum. And short circuit, ESC is short circuit current. On the other hand, maximum voltage occurs when the current is low or zero. The maximum voltage does not provide maximum panel electrical output power, but the power becomes zero because the current is zero. The maximum power generated occurs at curve of the curve which is called maximum power point or MPP. Fill factor is essentially a measure of quality of solar cell. It is calculated by comparing maximum power to the theoretical power that would be output of both of open circuit voltage and short circuit current together. The efficiency is most commonly used parameter to compare performance of one solar cell to another. Efficiency is defined as the ratio energy output from the solar cell, voltage time current, to input energy from the sun, solar irradiance times panel area. The operating point that must be focused are characteristics of circuit between the current and the voltage. Open circuit voltage is the difference of electrical potential between two terminals of a device when disconnect from any circuit. Short circuit current is current through the solar cell when the voltage across the solar cell is zero. When the solar cell is short circuited. That is parameter from the graphic. Maximum power point, a point where output power is maximum. It represents the bias potential with solar cell output the maximum net power. Now we see on left picture, two panels are connected in series by connecting the positive of one panel to the negative of the other. The result is double voltage, but the same ampere as on panel. For example, the graphic above, we have two 18-volt and 7.8 ampere panels in series connection. The output voltage is 36 volts. And output current, it's still 7.8 amp for series connection. As we see on the right picture, two panels are connected in parallel by connecting like polarity terminal together. The amperes are double, but voltage is the same as one panel. For example, in the graphic, we can see we have two 18-volt panel. The voltage constant and the current double. Solar system are made up of solar panel or solar module and solar charge or discharge controller, battery, and inverter. For the DC application, we can get from battery. Therefore, if electric energy needed for AC application, we need inverter convert the generated into AC from DC. And that is can be used for household. Now, there are some type of PV system. There are on-grid system is a grid dependent and off-grid system and hybrid system. On-grid system is depend on grid. Off-grid system, which is a system that works independently. Hybrid system, which is a combination of both off, on, and on, combination of both on-grid and off-grid. Now you see on-grid system. Solar power is connected to the utility power grid and depend on to the electricity grid. The output electricity from solar panel to the grid tie inverter merge to grid electricity to provide appliance. The excess power generated is sent back to the grid. Like the picture, this is inverter and joined together with the grid. The next off-grid system means the system works independently and it is not connected to any grid system. The system uses battery to store generated solar power. Hybrid solar system generate power in the same way. The system can work with grid or independently, but with using special inverter named hybrid inverter. The system is combination on grid and off-grid system. The system is still working even though the grid is being shut down. And when weather is cloudy, the system still can charge from the grid. How to maximize the electricity output? There are some rules to maximize the electricity output from a solar panel, such as there should be no shade on panel between 9 till 15 or 3 p.m. till the panel and angle equal to latitude. It should be never be tilt less than 5 degrees from horizontal. The panel should face north for the side which are south of the equator, and it should face south for side which are north of the equator. Mount the panel at least 10 centimeters above other surface, so air can easily cool the back of the panel. System sizing of the solar panel. For a solar photovoltaic system, the size of panel and battery must be matched with the energy need to appliance. Appliance use energy measured in watt-hours, and panels produce energy measured in watt-hours. In a solar system, if an appliance needs 100 watt-hours of a day to work properly, if only 80 watt-hours are produced by the panel, then the appliance will quit working early in the day. Calculate appliance watt-hour use each day. Always the calculate and the energy use on per day basis, because solar panel provide energy on a daily cycle. Calculate total watt-hours needed from the panel each day. Once the energy in the watt-hours used by a plant is known, the watt-hours that must be provided each day by the panel will be the total appliance watt-hour plus the watt-hour loss in the wire, battery, and controller. There's always some energy loss in battery, wire, and controller, around 30%. It is reasonable to say every 100 watt-hours needed by the appliance, at least 130 watt-hours must be provided by the panel. Determining the number of panels. Calculate the watt-hours per day produced by one panel by multiplying the panel peak watt rating, the panel generation factor, or sun hour. Divide the total watt-hours per day produced by one panel. The number of panels calculated by this number is the minimum number. Now, system sizing of battery is depend on, we can choose battery voltage system and capacity, and depth of discharge is DOD of battery is depend on the appliance and type of battery. The battery should store 5 times the energy the appliance use in one day, because we consider 20% depth of discharge. Now we can calculate size of the battery by compute watt-hours per day used by each appliance. total watt hours per day used by all appliances, multiply total per day by DOD or depth of discharge factor. For example, VRLI battery usually have 20%, so we can multiply by 5. But if we use depth of discharge of 50%, we just need to multiply by 2. Now the example of solar charging. Solar panel or solar energy is converted into electrical energy using solar panel. The electrical energy from panel is regulated by the current and voltage using solar charge controller to enter and be stored in battery. There are two types of the solar charge controller. Commonly used, such as SCC-PWM, pulse width modulation, and SCC-MPPT, maximum power point tracking. For maximum power point tracking, there are two types, such as a step-down regulator, voltage regulator, and step-up or booster voltage regulator. Now I share my experiment for solar charging. Use several model. Model A is charging the battery directly from panel to the battery, and model B charging the battery using DC buck converter voltage regulator. Model C is charging using SCC MPPT, and model D is charging using SCC PWM. The battery system has a voltage of 24 volt. Test carried out from 6 AM to 5 PM. There are some of tools and material that I use during the research, which are solar panel, SCC PWM, pyranometer, SCC MPPT, DC buck converter voltage regulator, battery, and wattmeter. These are some of the results that I have got. For solar irradiance, measurement by pyranometer, we get maximum solar radiation obtained was 900 and 900 watt per square meter at 11:55. More cloudy at 12 noon, and starting and decrease at around. This is the result. Okay, I think This is a result of the experiment. Dua menit ya.
We
Okay,
have around like 5 more minutes.
this
Ready? Thank you.
okay. This topic is interesting and quite popular nowadays. Will be better to understand if we also do practice some tests on the field, because the topic requires a lot of parameters that only can be seen doing measurement and tests like current, voltage, power, energy, and solar irradiance. This is some activity that we have done, such as design on PV system and solar charging for electrical bike. And the end, I want to say thank you for your attention at time. God bless you. Thank you.
Thank you very much, Mr. Widiharsa, for a very insightful presentation on the solar energy. I believe you all learned so much about it in a very short time. Even though my background is not engineering, I think this is a very interesting topic. While waiting for the questions, we still don't have the question now, but I am actually very curious. If you charge like for one day, how long it will the energy will be able to move the motorbike? Because just now I saw at the end of your PowerPoint, I saw the motorbike that are using the solar panel on top. So if you charge the motorbike for one day, how long it can be used to move the motorbike?
For the motorbike,
Yes.
yeah. I think Ibu Dini mau, I need help, Ibu Dini. Okay.
Yes, go ahead. Iya, berapa lama Pak satu hari ini kalau dicas dengan motorbike?
Untuk for the motorbike, it depend on the area of solar panel and how big of the battery.
Okay, also it depends on the
It is
area and
yes.
how big of the battery. And actually, we do have a question now from Central Philippine University, Glenn Fernandez. He asked, for 1 kW aggregate solar panel capacity, what deep cycle battery size in ampere hours is reasonable to acquire? 10 hours of sunlight? Is it required 10 hours of sunlight? Apakah perlu 10 jam, Pak, untuk ukuran 1 kilowatt?
If we use 20% depth of discharge, we times 5. Jadi kita harus mengalihkan dengan 5.
Oh, time 5. So how many hours is it?
For the capacity, untuk keawetan baterai, for long
for the long last
cycle.
use of the battery, yeah. So how many hours do you need for 1 kilowatt? Is it 10 hours or 5 hours, Pak? Kali 5 berarti 5 hours, is it?
Kilowatt is power, and battery is energy. Energy can store and save in battery. So it's depend on the penggunaan, ya, aplikasi penggunaan. If for long time, so the power is low. For the short time, the power can peak.
Okay, so actually it depends on the usage as well, not only how big the energy you can store, but it depends on the usage as well. So for Glenn Fernandez, I hope that answered your question. Actually, just now, as Mr. Widiharsa mentioned, it's good to practice, because not only about the theory, if you want to learn more about this, it's good to practice and doing your own. You can test like how many hours for the sunlight, because of course the amount of the light we get in our area might be different in Indonesia or in the Philippines, or it depends on the weather forecast as well. Sometimes it is not so sunny. So yeah. Beside Glenn Fernandez, is there any more questions for now? Maybe they are still absorbing about the topic that has been explained by Mr. Widiharsa. While waiting for some more question, we can open a Q&A session, maybe slightly longer at the end of our lecture. Let's continue with the next lecture by Professor Jeriel G. Militar, PME. He is the head of Mechanical Engineering Department from Central Philippine University. Professor Jeriel, without further ado, the platform is yours. Thank you.
Thank you, Ma'am Andini.
You're most welcome.
Good afternoon, everyone.
Good afternoon.
Selamat sore semuanya.
Selamat
I
sore.
hope I pronounced it right.
That's correct. Selamat sore. Thank you.
So let me share my screen. Okay, so this is the lecture number 2 for today under the International Collaborative Teaching. And I am supposed to discuss the experience of our university in implementing the technical elective subjects on energy management as part of the curriculum of Bachelor of Science in Mechanical Engineering program of the college. So the two topics actually under the energy management elective are solar and wind energy utilization. That's one subject or one course. And the other one is micro hydroelectric power. These are the two elective subjects that we offer in our degree program, Bachelor of Science in Mechanical Engineering. Now, elective because we are supposed to offer specializations in the general program of mechanical engineering. However, because we do not have enough faculty and enough number of students, we cannot offer a number of elective or specializations. So we just choose these two because we have experience in implementing solar and micro hydro projects under our Renewable Energy Center of the college. So for this lecture, I decided to focus on micro hydroelectric power since Mr. Widi has already discussed on solar. So I decided to discuss only the basics of hydroelectric energy. You see, micro hydroelectric power is a one-semester course, and it would be very difficult to compress everything in one session for 30 or 35 minutes. However, I will try my best. So let me start with the basics, the definition, let me start first with the desired outcomes for this lecture. We usually tell our students before the start of the course the desired outcomes, so they will know what to look for during our lecture. So at the end of this lecture, it is hoped that the participants would be able to describe the process of estimation and conversion of water power to electric power. Apply the water power formula to estimate available water power from a water resource. Name the different hydro schemes and categories and enumerate the components of a micro hydroelectric power system and describe the design and implementation processes. This sounds a lot, but I hope we would be able to attain these objectives for this lecture. Now, the topics covered in my presentation would be country backdrop on hydro energy. I have quickly also included the hydro potential for Indonesia for the benefit of our audience. So I will also discuss what is hydroelectric energy, how is it produced. I will discuss very briefly simple water power calculations, and then hydropower schemes or categories adopted by our Philippine Department of Energy. And also will discuss very briefly the designing process of a micro-hydroelectric power system. And of course, other related topics if we still have time. Okay. So the Philippine Renewable Energy Program adopted by our Department of Energy actually they have adopted this acronym, no? Big Show. So it will be easy to remember, no? BI for biomass, G for geothermal, S for solar, H for hydro, ocean, and then wind. So that's Big Show. So now we will discuss the hydro. In the Philippines, the total untapped hydropower resource potential is estimated at 13,000 megawatt, of which 85% are considered to be large hydros and small hydros. That's amounting to around 11,000 megawatt. And then 14% are classified as mini hydros, and then 1%, less than 1%, are considered micro hydros, or 27 megawatt, total of 27 megawatt. At this point, let me insert the potential, no, of Indonesia. Since Indonesia is much bigger than the Philippines, no, the Indonesia's technical hydropower potential is actually more than 5 times that of the Philippines. Okay, so it's estimated at around 75,000 megawatt. Now, that's a lot of power, with untapped resources concentrated on the islands of Sumatra, Java, and Sulawesi. These are big islands, and they have very good watershed areas. So the hydropower potential is very large. No, hydropower is the biggest source of clean energy in Indonesia today. At the end of 2021, a total of 6,601 megawatt, or about 6.6 gigawatt of hydroelectric power was produced across Indonesia. So that's the picture of hydropower in the Philippines and in Indonesia. So what is hydroelectric energy? It is, of course, electricity produced or generated from hydro energy. And what is hydro energy? It is the energy present in moving water. Okay, so there's the picture of a usual schematic of a hydroelectric power generation. No? You have the water potential here, water, and then it is conveyed through a penstock to a turbine where the energy, kinetic energy of the moving water is extracted or converted into mechanical energy through a rotating shaft, which also drives the generator to produce electricity. So that's the simple schematics of producing electricity from hydropower or power from moving water. So turbine is the device used to extract the kinetic energy from the moving water. Okay, so let's have a closer look at the equipment. No, so the impact of moving water on turbine blades cause the shaft of the turbine to rotate. You see here in the picture, no? The blades are connected to a shaft. So the rotating shaft driven by the turbine now drives a generator either through a common shaft or through a power train. They can use belt and pulleys, gears, or chain and sprocket to convey the power from the turbine to the generator. So of course, the generator, we already know this, is a device that converts the rotating shaft power, mechanical power, to electrical power. So that's how hydroelectric energy is produced. Of course, for the information of everyone, these are the most common types of turbines being used in our hydroelectric power systems. We have the Francis turbine, the fixed pitch propeller, turbo, Pelton, Kaplan, and crossflow. And there are other combinations, depending on the designer of the microhydro system. So how do we determine the power available in a water resource, or gross water power? So of course we know this as engineers know this. Energy released is equal to mass times gravity times height, where m is mass, h is head, and g is gravitational acceleration at 9.8 meters per second squared. So the mass of water in this formula is equal to density, usually labeled as rho, times its volume, V. Okay, so rho is assumed at, this can vary, but very, very small amounts. The usual value used is 1,000 kilograms per cubic meter. That's the density of water, standard density. So energy released now would be equal to volume times density times gravity times h. So water enters at the turbine at a certain flow rate. So that is, the flow rate is now Q, which is equal to volume times volumetric flow, the flow, the volume of the water times gravitational acceleration. So the gross power from water now is equal to rho times G times rho times Q times G times H. Okay, so that's the gross power formula used to determine the amount of power available in a water resource. Take note that the water resource is always considered to be moving water before you can extract the energy from the said resource. Okay, now that is gross. Now, what about the net power from water? Of course, before we can use the electric power, it has to go through a number of from the turbine to the generator. There are power losses in along the way. So the total losses, as per experience of micro hydropower implementers, could amount to a maximum of 50%. So if, for example, the maximum gross water power, the gross water power would be 1 kilowatt, the net power would just be 50% of that. So around 500 watts. That would be the usable electric power at the end of after the generator. So for those implementing micro hydro energy projects, the formula is simplified to be something like this. Power net is equal to power gross times 0.5. That is 50% of the gross water power. So P net is equal to Q times H times 5. So it's easy to remember for implementers. Just remember the formula Q times H times 5, where Q is the water flow, H is the height, available height, and 5 is the constant that represents the Q, the G, and the percentage, which is the efficiency, which is 0.5. So 10 times 0.5, that's 5. So Q times H times 5. Okay, so sample calculation for the gross water power. For example, you have been asked to design a microhydro scheme to supply 50 kilowatt to an upland barangay or village. There is a waterfall nearby which is 20 meters high. How much flow is needed? Okay, so the barangay needs around 50 kilowatt of electric energy or power for their needs. So there is a waterfall nearby, 20 meters high. As a mechanical engineer, you are asked to check whether this is enough to supply the power requirement of the barangay, which is 50 kilowatts. So how much flow is needed for the waterfalls such that it can supply 50 kilowatt of net power. So using the formula P net or net power is 0.5 times H times H gross times Q times 10, or the simplified form is H times Q times 5, because 10 times 0.5 is 5. So HQ times 5. So Q is, of course, the P net divided by 0.5 times H gross times 10, or 50 kilowatt divided by 0.5 times 20 times 10, or the resulting water flow needed is, of course, now at 0.5 cubic meter per second. So the waterfall should have that minimum flow of 0.5 cubic meter per second for the waterfall to be able to deliver the required 50 kilowatt of power by the village. So that's how you apply the simple water power formula to estimate what the available power from a water resource. By the way, cubic meters per second is equal to 500 liters per second. For those who are not familiar with the conversions, okay, because 1 cubic meter is 1,000 liters. So 0.5 is 500 liters per second. Okay, so let's now go to the hydropower schemes. No? There are two main hydropower schemes actually. One is the water impounding scheme, and the other one is the run of the river scheme. For water impounding, as the picture, as you can see in the picture, there is a big dam that is used to store up water, no, at the upstream of a river. No? So this is the water impounding. And the run of the river system just uses the natural flow of the water resource to produce, no, to produce the power needed. So what is extracted is the kinetic energy from the natural flow of the river, only that it is diverted and dropped down to a penstock to the turbine. While for water impounding, water is stored, no, in a reservoir, so that's there will be enough water supply to produce larger amount of power at this point. Because if you look at the illustration, for the run of the river, you will not have enough water resource to supply large amount of power because it is dependent on the natural flow of the water resource. While for water impounding, you have a lot of water impounded or stored, so you can generate a lot of water power from this water resource. Okay. So of course, there is also a hybrid or a combination of this where the excess power generated by the hydro system in this large hydro system, for example, if the demand for electric power is lesser, no, I mean not so much as the energy produced by the system, some of the power is used to pump the water back up to the reservoir. So it will again have enough water power to be used in case the demand is greater for electricity. So that's the pumped up storage system for hydro. Okay, so in the Philippines, our Department of Energy has categorized hydropower schemes depending on its capacity. No? So the biggest is the large hydro. It's called the large hydro, and it has capacities of more than 10 megawatt. Okay, so it uses water impounding, no? Because they need a lot of power. 10 megawatt is a lot of power, so they need to impound the water resource, so they will have enough water to supply the energy demand. So usually, 2 or more water sources or a large watershed is involved, no, to be able to impound the large amount of water needed by the system. And the water uses at this point for large hydros can be both for domestic irrigation, power generation, and recreational. These are actually the hierarchy of water uses, no? Because the use of water can be domestic, meaning it can be used as drinking water in the households, or for bathing, etc. No? Household use. The next priority is the irrigation. Water can be used for irrigation. And power generation is only the third priority in the use of water resource. So I hope, or I don't know if this is the same water use priority implemented in Indonesia, but in the Philippines, this is the hierarchy. No? If the water source is enough just for domestic, then it will be used only for domestic. If there is enough water for irrigation, then after domestic, it can be used for irrigation. And then the third is power generation. So if the water resource is not enough for the first two, then you cannot generate power. You cannot use the water resource for power generation because it will be prioritized for the first two uses. And last would be just for recreation or for tourism. So for the next category, it's the small or mini hydro. Our DOE has classified that small or mini hydro. The system that has a capacity of 100 kilowatt, 101 kilowatt to 10 megawatt, up to 10 megawatt. So if the capacity of the installation is up to 10 megawatt from 101, then it is categorized as a small or mini hydro. The same water uses as in large hydro, and still uses water impounding. Because if it's around 2 megawatt, 10 megawatt, then it's still a large of power and needs a lot of stored water. Okay, the next category, the third one, is the micro hydro. Okay, the capacity of this system is from 1 kilowatt to 100 kilowatt. Okay, so this the picture you can see. This is now run of the river scheme. No, there is no large water impounding. The natural flow is used and diverted for a while and then dropped to a penstock and the turbine. So usually the water uses involved are irrigation and power generation. And then we have the fourth, the Pico Hydro, which is the smallest. Capacity is less than 1 kilowatt. It uses run of the river, usually streams or canals, irrigation canals can be utilized. Only one water source. It's either for power generation or for irrigation. So you can see at the picture, there is not much height that is needed. Only this one system is around 1.5 meter, only. The drop is only 1.5 meter. And this size could, I think, produce 200 watts of electric power from this water resource. So that's the smallest, the Pico Hydro. Okay, so what are the micro hydro system components? The usual components of a micro hydro system, take note that a micro hydro system is only a run of the river scheme, run of the river. So there is no impounding. What we have is only the intake weir or a very small dam, usually 1 meter height of a dam that is used to divert water from a stream or from a river to a canal, or channel, or head race. Those are the technical terms used to refer to the diversion canal used to divert water from the source to a point where it can be conveyed through a penstock to be dropped to a turbine where it is extracted and used to generate electricity. So these are the usual components. We have the intake weir here, and then the settling basin. Settling basin is right there also. It's necessary to have a settling basin to have the water silts and other impurities settle down before it is conveyed to the channel and the penstock. Then we have the channel or the head race. We have the forebay, this one here. Okay, that is a very small water stacking, impounding before it is dropped to the penstock. And then, of course, the powerhouse where you have the turbine, the generator, and the load controller. And then from there, it is either directly used or distributed to households, or it can be fed into the grid, electric grid. Okay, so what are the stages in designing a micro hydro system? We usually give this to as part of our course because we know this can be used later by our graduates when they go to the field. They can actually design micro hydro systems themselves for villages. So the stages are: first, capability and demand survey before they can design the actual system, micro hydro. They have to do capability and demand survey, and then the hydrology study and site survey, followed by the pre-feasibility study, and then the full feasibility study. Now, the capability and demand survey, the first stage in the design process, is done to assess the organizational capability of the target users. Usually, these are villagers or people in the rural barangays. There is a need to assess the organizational capability of the target users because micro hydro is often planned for rural or remote off-grid communities where people do not have people have less technical capabilities. Unlike in cities, of course, and in big towns, you have people who can have the technical capabilities to operate the system. While in rural areas, you need to identify and train people to do that. So the project also involves a large initial capital investment, and the construction and installation is also labor intensive. So there is a need for training of locals for the operation and maintenance. So that is covered in the capability and demand survey. So for the hydrology study and site survey, this one establishes the hydropower potential of the site. Okay, so the designer goes to the site, assesses the hydropower resource, measures the height, the flow, etc., shows the annual water flow variation, locates the optimal siting or the optimum siting of the components. Where can the diversion weir be placed in the water resource? How long would the channel be or the diversion canal? And where is the best location for the power plant? Okay, so these are the things that are done in the hydrology study and site survey. So pre-feasibility study, after gathering the results of the demand and capability survey, you match that with the results of the hydrology and site survey. So if in the capability and demand survey, you have established that they need around 20 kilowatt of power, you match that with the hydrology and site survey. Can the water resource in the community supply the needed amount of power, 20 kilowatt? Now, so here you do the matching of the resource with the demand of the target users. Okay, so it also includes, of course, more than one engineering design option. We do not always do one design or one option for a project because, for example, in the community, it would be possible that it's better for them to use diesel genset than build the micro hydro, because if the cost is beyond what the barangay or the village can afford, and they do not have that much demand for power, then probably just buy a diesel genset is the best option. Or maybe the barangay is not far from the last distribution post of the electric grid. So it would be better probably to just connect, by the extension wires and connect to the last electric post. So those are the design options that the designer needs to look at before finally deciding to implement a micro hydropower scheme. And of course, the full feasibility study should be done after the pre-feasibility study has determined that the project is viable. So in the pre-feasibility study, the initial design calculations are done. So in the full feasibility study, the actual engineering designs are now done, including financial study, using economic indicators, the income of the barangay and so on, whether the income of the people in the barangay can sustain the operation of the microhydro system. So for designers, the golden rule of the feasibility study is always O&M first, meaning operation and maintenance, economics and plant factor second, and then engineering design is last. So the detailed engineering design is done last because the designer has to determine first whether the operation and maintenance can be done by the barangay or the cost is sustainable, and then the economics and plant factor are viable or desirable for the said system. So very briefly, let me discuss the plant factor and the load factor, as these are important factors in the design of the microhydro system. So plant factor, also called capacity factor, is the ratio between the actual energy used versus the actual energy available. While the load factor is the ratio between actual energy used versus the load connected. So take note, the only difference is the denominator. Energy available, while here is the load connect. And of course, energy is defined as power used over a period of time. Sometimes laymen are confused with the kilowatt and the kilowatt hour, the power and the energy. Power is, of course, kilowatt. We refer to 5 kilowatt, 1 kilowatt. That's the power, for example, of your light bulb. I am using 100 watts. That's power. Energy, on the other hand, is the power times the length of time that power is used. So it's kilowatt hour or watt hour. So if you are using the light 100 watts for 1 hour, that's 100 watt hour energy. So the 100 watts is the power, while energy is 100 watt hours. Okay. So do I still have time, Andini?
Yes, another 5 to 10 minutes.
Okay. So let me very briefly just give this case study. CPO AREC installed a microhydroelectric plant to supply electrical lighting for a remote barangay. The scheme costs 500,000 to install. The total number of households in the village was 50, but started with only 25 households connected to the plant. It's consuming 200 watts. So one household consumes 200 watts. The other 25 households in the barangay decided to wait and see. Okay, only 25 connected initially. So the installed microhydro power can provide the 50 households with 200 watts of power each. So in the first 5 years, the first 25 households which were initially connected were using their lights only from 6 p.m. to 12 midnight. That is only 6 hours of the 24 hours the plant is running. So the plant factor was 200 watts is 0.2 kilowatt times 25 households times 6 hours divided by the total capacity of the plant, which is 10 kilowatt times 24 hours. So that's the total energy generated by the power plant, 10 kilowatt times 24 hours. So the plant factor is only at 0.125. Okay, so in the next 5 years, the wait and see households decided to connect, bringing the total power consumed to 10 kilowatt. So there are now 50 households connected after 5 years. So power factor would now be 200 watts times 50 households times 6 hours. So it has doubled. Plant factor has now doubled to 0.25 from 0.125. Now, the economics. Suppose the 500K was loaned and the bank charges interest and expects a repayment of 100,000 per year for 10 years, repayment of the loan. Since the first 5 years, only 25 households are connected, the yearly cost per household is 100,000 divided by 25. So that's around 4,000 per year per household. Or per month, that would be 333 pesos. So after 5 years, the remaining 25 households connected. So the yearly cost per household is now 100,000 divided by 50. So there are already 50 households sharing the cost. So it's now 2,000 per year per household, or reduced to 166 per month per household, which is now affordable for the rural household. So from the case study, if the 25 households use their lights for 6 hours, excuse me, the total energy used is 25 households times 200 watts per household, excuse me, times 6 hours. So that's 30 kilowatt hours. That's energy, no? 30 kilowatt hours. So the total energy capacity connected to the households is 120 kilowatt hours. So the load factor is 0.25. That is double the plant factor. If the 50 households were connected, of course, it will double. Load factor will now be 0.5. Okay. So for economic considerations, the more the plant factor or capacity factor approaches 1, the better. So the designer should aim for a higher plant factor or higher load factor. So the key design rule for microhydro therefore is design for the highest possible plant and load factors. So, okay, so that's all for the basics of hydroelectricity. Terima kasih semuanya.
Sama-sama. Thank you so much, Professor Jeriel, for a very insightful presentation on hydropower. At the beginning of the year, this lecture, we learned about solar panel and now hydro. So both of the country, Philippines and Indonesia, we are lucky that we are blessed with the abundance of lights from the sun and also surrounded by water. We have lots of body of water in Indonesia and in the Philippines. I believe all of our students learned so much from this lecture. Okay, we are still waiting for the question. If you have any question, please kindly type in your questions in the Zoom chat box. Or if you want, you can ask directly to both of our lecturers today. You can raise your hand and ask question. Okay, while waiting for the question, just now I take some notes that the hydropower is actually from the moving water. The energy is extracted from the moving water, so it's not possible from the still water. But the height is only 1.5 meters. You can extract the power already. So it's actually very useful. You can do it anywhere, right, Professor Jeriel? Professor Jeriel? Can you hear me?
Yes, ma'am. Yes. Come again.
Yeah, just now I take notes that the hydropower, the energy can be extracted from the moving water, but the height required is only 1.5 meters. So it can be done anywhere actually.
That's for the specific system for the Pico Hydro actually, where the turbine type uses a propeller, and it needs only 1.5 meter drop of water for it to be able to generate hydropower.
All right. So you do need a propeller.
Uh, Traditionally, it's always required that there is a drop, of the water. However, recent developments, now they have turbines that can operate even at stream flow. No need to drop the water.
All right.
Just like wind turbines, there is no difference in height needed. Just the flow of wind. Now, in the same case for turbines that do not require water drop, just the stream flow itself, they place the turbine there, and because the water is flowing, there is still that kinetic energy present in the flowing water. So kinetic energy at that point can already be extracted by the turbine that was placed in the flowing stream of water. Okay.
Very interesting. Thank you so much. So beside propeller, you can also just use the turbine for the
Yes.
flowing water. Actually, the propeller is used for the engine for the aircraft. So
Yeah.
it is actually very interesting.
The same principle.
Same
Yes.
principle, yes. Thank you. And for all the students, do you have any questions? You can ask the questions in Bahasa. I can help you to translate. Ada pertanyaan? You can ask the questions in Bahasa. You can raise your hand if you have any questions, or type in your questions in the chat box. Or any discussion. We still have some of our lecturers joining. Do you have any discussion or questions? Pak Widi, ada diskusi atau pertanyaan?
I have a quick question for Mr. Widi, if it's if it's
Go ahead.
allowed.
Go ahead, please.
Because in the Philippines, the main challenge or difficulty in the use of utility scale solar plants, the big solar power plants, like this ground mounted solar power plants or solar farms with the capacities of 20 megawatt, 10 to 20 megawatt capacity of solar power plants. The challenge is for the grid, the national grid. There is a cap, to a capacity that the grid can take in from solar power plants, because you see the grid has to maintain stability of power supply for its users. And since solar power plants are intermittent generators, meaning it cannot supply a stable amount of power for a longer period of time. Especially it's a big plant, maybe maximum of 6 hours a day or 8 hours a day of production, and that is interrupted if there are clouds that go above the panels. So that makes the supply not very reliable. So that's the challenge for the grid. That's why our grid limits the amount of energy that it can take in from solar power plants, to be able to maintain the stability. Do you have the same challenge in Indonesia?
All right, thank you so much, Pak Widi. Maybe I'll try to translate. Jadi, the solar panel is not really stable. Jadi nggak terlalu stabil gitu ya, Pak Widi ya. Karena harus ada 6-8 jam. Apakah solar panel ini bisa stabil? Karena kan memang harus ada gridnya berapa, minimum grid gitu, Pak. Is it a stable energy, this solar panel? Silakan Pak Widi, thank you. Masih di mute Pak Widi, tolong di unmute. Terima kasih.
Oke, terima kasih. Thank you. Maybe I will screen. I have experience for my 2000 watt peak in my home. This is how much energy we can receive from the sun. In Malang, although tropical climate, but very rainy, very rainy and cloudy. Then Surabaya, that's not too far, but Surabaya is a beach and have more solar intensity. Now we can for solar energy per square meter, sometimes too low, like this, sometimes too low. If we get normally like this, 6 kilowatt hours per square meter, and that is combination for on and off grid. I think that is needed. Maybe that is my opinion.
All right, so minimum is 1 kilowatt per meter or per hour, is it? And maximum is 6. So you can combine this and you can use it for the whole day, is it, Pak Widi? Bisa satu harian ini ya Pak, stabil.
Yeah.
Even though Malang is very cloudy.
And I can show the sun hours. In Malang. Sometimes only 2 hours and maximum 4 hours per day.
Because Malang is very cloudy and always
very cloudy, and not depend only latitude of location, but the climate also contribute
to this, yes, the climate. So is it stable enough to be used in every day? Cukup stabil ya Pak, setiap hari?
For a long period in a year, I think sometimes we need a battery, sometimes we need a solar panel.
All right, so you need to combine. You need to have a backup. You have a battery and also solar panel. So once we have a lot of sun, like recently July, August, and September, we absorb a lot of the energy from the sun, and then we keep it in the battery, and we can use it during the month of October, November, and December when the rain, we have a lot of rain.
Yes.
Those months.
Okay.
All right. Thank you so much. Is there any more discussion or questions? All right. I think it's very interesting to learn about solar and also hydropower today. Even though my background is not engineering, I learned a lot today. I believe our students from the Faculty of Engineering also learn a lot. Thank you so much. Before we end this lecture, can we please take our group picture for everyone? Can you please turn on your camera and use our background that I have shared earlier? So Professor Agus, thank you so much. The Dean of Faculty of Engineering joining. I saw a lot of our lecturers. Bu Ike still driving on the way. We have Bu Delila and Dean Danny. Thank you so much for joining. Miss Kay, welcome back. And we have Vice Rector Rudy Haryanto and also Vice Rector Pak Sunardi and Pak Rudi. And okay. Let me just, everyone, all of our students, can you please turn on your camera? I'll take your picture now. Okay, 1, 2, 3. One more, 1, 2, 3. Thank you so much. I will see you in 2 days' time, actually. I'll see you on Thursday. Thank you. Bye-bye. Thank you once again, Professor Jeriel, and thank you so much, Mr. Widiharsa, for sharing with us about the solar panel. And thank you, everyone, for joining. Thank you. See you again soon. Bye-bye. Thank you. Bye. Thank you.
Bye-bye.
Thank you, Jeannie. See you
You're most
again.
welcome. See you again. Bye-bye.